So last time we have seen the stability analysis of Crank-Nicolson method by Lax-Richmond theorem. So now we will see the same stability analysis by von Newmann method. What is the advantage of this method is, first we should know that what is the advantage of this method is, here we don't bother about the convergence of the matrix, because last time the Lax-Richmond theorem tells that the method is stable if and only if it is convergent, but here we don't have to bother about the convergence of the matrix. So that is why this method is a little bit more useful than the Lax-Richmond theorem. So here, so first let's write the Crank-Nicolson scheme. The Crank-Nicolson scheme is minus R U I n plus 1 plus 2 plus 2R U I n plus 1 minus R U I plus 1 n plus 1. This was equals to minus R, so R into U I minus 1 n plus 2 minus 2R U I n plus R into U I n. So this was the finite difference scheme for the Crank-Nicolson method. So again we will do the same. We will just subtract this to the guess solution, to the solution what we are obtaining from our method, that so this will be minus R un plus 1 I minus 1 plus 2 plus 2R ui n plus 1 minus R ui plus 1 n plus 1 bar equals to the same thing with the bar. So this is your computed solution. So computed. Again what we want, that the error, so the error will come. So if we'll subtract these two, we'll get minus R error at I minus 1 n plus 1 plus 2 plus 2R error I n plus 1 minus R error I plus 1 n plus 1. This is equals to R error I minus 1 n plus 2 minus 2R error I n plus R error I plus 1 n. So this is what we are getting, the FDM scheme of error. From the FDM scheme we are getting that what the error will be. Okay. So now what we will do, we will just apply here. So here I'm not going to discuss the theory behind the method. So let's see that what I'm going to do. We will substitute this error, these errors by Fourier coefficients. Okay, so this will be substituted by the error m at nth place will be substituted by the Fourier coefficient AR, some factor zeta n into exponential square root of minus 1 beta R mh. So this h is your step size in space, step size. Now here AR is some constant. This xi is called amplification factor and this beta r is defined as r pi r pi divided by nh. Okay, so see, here we have a bunch of the error is the error is the sum of the bunch of the coefficients. But for the simplicity, what we will do, will not consider the sum, because see, if this satisfy the equation, since this is satisfying this equation, and this contains many terms, and this is homogeneous, so it means that what, if you take the individual, the sum, see, sum is satisfying this, so it means that the individual will also satisfy this. So instead of taking the sum, we'll take any term, let's say this term, we'll take only a, we'll not take the sum, we'll just take a zeta n exponential minus 1 beta mh. We'll just take this and we'll see that what happened to the solution. So let's consider this, that the error as this. So we'll consider the error at mn is equals to a zeta n exponential. So the error at mn is equals to a zeta n and exponential minus 1 beta mh. So a zeta n exponential minus 1 beta mh. Okay, so now we will substitute this to the last equation, to the error equation. So let us substitute this to the error. So this will give me a minus r a zeta n plus 1 exponential square root of minus 1 beta I h. So it was I minus 1h plus 2 plus 2r a zeta n plus 1 exponential square root of minus 1 beta ih minus r a zeta n plus 1 exponential square root of minus 1 beta I plus 1h. This will be equals to r a zeta n exponential minus square root of I beta I minus 1h, and then plus 2 minus 2r a zeta n exponential square root of minus 1 beta ih plus r a zeta n exponential square root of minus 1 beta I plus 1 and 2h. Yes. So what happened, that a will be cancelled out, then zeta n will be cancelled out from all. So the zeta n will be cancelled out from all. So here we are remaining with a. So let's write it in the different manner. So we'll write minus r zeta exponential square root of minus 1 beta. So see, I minus 1 is there and I is there, I minus 1 is there, I plus 1 is there. So let's cancel the I factor will cancel out. So here minus 1 will be remaining, so it will be minus 1h plus 2 plus 2r zeta, and this I will be cancelled, minus r zeta exponential square root of minus 1 beta h. This would be equals to r, and zeta won't be there, so exponential minus square root of minus 1 beta into minus 1h plus 2 minus 2r, that's it, zeta won't be there, plus r into exponential square root of minus 1 beta h. So from here I can write, so if we'll club these two terms, so this two term is nothing but minus r, zeta will be there, and 1 by exponential square root of minus 1 beta h plus exponential square root of minus 1 beta h. So this I can write cosine of beta h, and similarly if we club this term and this term, we'll get cosine of beta h there also. So what we are getting, let me write it. So we are getting minus r, so I'll erase this. So we are getting minus, so finally we are getting minus r cosine, this will be 2 cosine, so it will be, this would be 2 cosine beta h. So minus r, so minus 2r cosine beta h, and zeta will be there, plus 2 plus 2r zeta is equals to 2r, zeta won't be there this time, only that cosine would be there, so cosine of beta h plus 2 minus 2r. Okay, yes. So if we calculate zeta from this, so zeta is coming 2r cosine beta h plus 2 minus 2r divided by 2r minus 2r cosine of beta h plus 2. So this is the zeta that we are getting. Now see, the von Newman stability analysis tells me that this method will be stable if, so the method will be stable, if the mod of zeta will be less than 1. So again we are on the same stage, 2r cosine beta h plus 2 minus 2r divided by 2r minus 2r cosine beta h plus 2 is less than 1. And again we are on the same stage that since this we have already seen that this is always true, this is true for every r greater than 0. This we have seen in the Lax-Richmond stability analysis in stability analysis. So this we have already seen. So hence this Crank-Nicolson is also, from one Newman stability condition we observed that Crank-Nicolson is unconditionally stable. Okay, thanks.